Hi, this is going to be our paper presentation on scaling autoregressive multimodal models, pretraining and instructing tuning, also known as Chameleon. This paper was written by Lily Liu, Owen Shi, Ramakant Basanuro, and many others. It will be presented by Michael Cruz, myself, Christopher Lee, and Saurabh Agrawal. Our problem statement today is going to be, at the time of this paper's writing, there were very few computationally efficient models that were good at both writing from text to image and from image to text. The current approach at the time was diffusion models, which was very good at producing results computationally efficiently, but not having state-of-the-art results when compared to another method known as autoregression, which had better outputs but was also computationally expensive. The aim of this paper is to take the best of both worlds and have a computationally efficient algorithm that can deliver state-of-the-art performance for generation for image to text and text to image tasks. Now, how exactly is that doing that? Well, we have a model here known as Chameleon, which is a retrieval augmented token-based decoder-only multimodal language model. This means it's retrieving tokens from memory and it's decoding using a model that works bidirectionally from text to image and image to text. It can infill and generate both of those modalities, and one of the benefits to this approach is that its data can be upscaled at an exponential scale and has a more diverse data set than previous approaches. Its pre-training uses something called retrieval augmentation, which we'll get into in a moment here, using that fancy new data set to give better results. This pre-training phase is followed by a supervised fine-tuning phase, giving it multitask capabilities that was normally seen on text-only models but hasn't been adopted to a combination text-image modality. This makes it able to take an input as text, input as image, or a combination of both for a variety of tasks involving image and text. And what exactly are these tasks that it can do? Well, here's Chameleon, and here's the first task. The first is going to be text-guided editing. We see here at the top, there's a picture of a woman, followed by a caption that says, "Make her an alien." And what the model's going to do is it's going to turn that woman into an alien. And then we're going to have another task called image-to-image grounded generation, which takes in a baseline image acting like a scaffold as a baseline image that is also fed in with a caption to modify that image using a specific style rather than just a specific change to the image. In this case, we have a childlike drawing of a bird, but then on the right it says, take this drawing and draw a kingfisher from this scaffold image. This can be extended to not just outlines like in this bird example, but also to pose examples where it's fed an example pose followed by a posed person, followed by a description of the pose. See here that we have on the right there the bird, and we also have this woman in a yoga pose. Another task this model is particularly good at is spatially grounding, which means that it can take in an input statement and define the location of certain objects and output an image with those objects at those locations. We also have a task called how to write, which is better at writing text. Here's the output of both of those things. Here, note that the how to write task is producing output for a word. The lettering isn't spelled completely right. It says morning rather than morning, and that's but the idea of the word is there and the letters are discernible, which is quite remarkable. Also note here that for the spatially grounded task, there is a refrigerator at the location described, as well as a stove. And finally, we have some tasks that we're used to seeing, just some typical image-to-text tasks, including captioning, visual question answering, and reasoning. Here on the left, there is an image followed by a caption for the image, which is to describe the given image, and it'll generate a caption, which here is a beautiful view of a city from across a river. For the VQA, it's going to give a question about what time of day the photo is taken, and it says sunset time, which is a pretty good guess given the context of the image. Now, how exactly is Chameleon doing all of this? Well, there are 3 phases to it. The first is the pre-training phase using RACM3. Then this phase is followed by contrastive decoding, and then supervised fine-tuning. Now, what exactly is RACM3? Well, to talk about RACM3, we have to talk about CM3, which is a causal multimodal model. Causal multimodal model is all about the causal action. In this case, for GPT models, the typical GPT model uses a causal mechanism, which means that each token that is predicted by the model is dependent on the previous tokens, but none of the future tokens. So as this model is trained, it is using the previous letters, the previous tokens, to predict what the next token will be. But it doesn't have the ability to see into the future, and can't, for instance, generate what this hyperlink to a particular Wikipedia article will be based on the word in the future. In this case, this hyperlink would have been a link to Armenian nationalism, but for the model to get there to the word that this link depends on, it'd have to see into the future, which this just can't do. There have been attempts to fix this using models like BART, which add a mask on top of the words of interest and essentially bidirectionally encodes it to be causally predicting from left to right instead. So as the model trains, instead of learning what came before it, what came after it, it's guessing what the mask could be underneath. And this can work. It's only about 15% effective for decoder-only structures. So it is doing what the task sets out to do, but it's not effective at predicting what this hyperlink will be given a future token. That brings us to the next and final iteration of this, which is the causally masked language model. What it does is it masks the hyperlink in the same way that the bidirectional masked language model is doing, but rather than having the model learn by guessing every time, we also attach the definition of the mask to the sentence so that the model can learn at the end. It has all the information it needs for every single sequence that it receives. And that teaches the model quite efficiently. Well, not efficiently, but it teaches the model, and it learns far greater than 15% of the masks that it's fed. And the only problem with this is the length of this is quite long. The mask has to be attached to the end, and these extra mask tokens have to be accounted for, because these masks are not limited to one per sequence. You can have multiple masks per sequence to teach the model on longer captions, because a caption is not limited to one sentence. See here that we have a mask for this first hyperlink, followed the mask to the end of the hyperlink, and at the end we just attach them as like a dictionary lookup for each hyperlink. You see here mask 0 corresponds to the first hyperlink, mask 1 corresponds to the second. The solution to this is to, instead of storing all of the parameters within the solution to this is, instead of storing all of the data in the data and storing that data within the parameters, we're going to attach these sequences to an external memory. Take example here, and this is what's called retrieval augmented CM3. We take in an input statement, we pass it into a retriever. This retriever looks within its memory and tries to find similar documents. Documents are images, texts, or a combination of both. Finds a document that is similar to the input sequence and outputs that into a generator. And having it all stored in this memory is far more computationally efficient than storing the parameters of every sequence within a neural net of some sort. This instead just keeps it all into a separate memory and compares it as the models are fed in during inference phase. Now, what exactly is this retriever doing? Well, here's the nitty-gritty of it. We have an input fed into the known as the query document that's fed into a mixed multimodal encoder, and this encoder is an extension of CLIP. It's using a couple of techniques. It's using mean pooling. It encodes the text into a common vector space, and in the memory, think of the memory as an array of those documents that we talked about, and for every piece of memory in that array, we're going to compare it after encoding it by calculating a cosine similarity. So we have our query document, and we have an array of memory documents. Each one of those we compare to the query document. And after it's compared, we have another array that's going to act as our output that keeps track of the similarity scores, and this is sorted by highest similarity. As that's passed out, this represents here our output array. Note here that it can be both a text, it can be an image, then it'll be fed into the generator. Now, what exactly does it look like going into the generator? Well, here's an example. First, we have a caption, then we have the image. They're separated by a break token because the two vectors are put into the same space and they have to be differentiated by some way. And the way they're doing this is by separating caption first, followed by image. And because multiple documents, there is a threshold for similarity. So that means more than one document can be fed at the same time. What actually gets passed is going to be the input sequence, which was that sentence that we saw at the beginning, followed by a list of retrieved documents with a similarity score above a certain threshold. So take, for instance, this could be our input sequence, and if it was passed with an image, this would also be part of our input sequence, and everything after this will be our retrieved documents based on a similarity threshold. They are separated by break tokens and distinguished as a set of documents using an end of sequence token. Those will be passed into the transformer like this, into this portion here, the transformer. Every retrieved document will be passed into the transformer, and they will be encoded, they will be decoded, and their loss compared to the ground truth using a FID score will determine their loss. We'll talk a bit about the loss here in a second. For the main document, the input sequence generates an output as well using this transformer, and then a loss is calculated there too. Here we have the actual function of it, the loss function. It is a combination of both the main function, the main document, with the retrieval document, as well as this variable here, which is a scaling factor to increase the relevance of the retrieved documents. The idea behind this is to get the model to get used to using the retrieved documents and to put more emphasis on the output of these documents rather than the output of the output generated by just the sequence. Expanding this further, we see here that the loss for the main document is a logarithmic function and a conditional statement here. Pay extra attention to that here. This x variable is the output. This output here is dependent on the masks that are found in that input sequence. And what's subtracted from those is this function here, which is log p of the retrieved documents. And rather than it being dependent on the output generated, because the output generated is just the documents and sequences that were stored in memory, we're only training the model's loss on the masks that are added to those documents. We're also adding a scaling factor to it to make the model more inclined to use these documents when generating an output. The only problem with this though is that because we're dependent on generating from retrieved documents, the model is not so good at generating brand new content or generating content given a zero-shot context. So the alterations that were made to this architecture, CM3, are first they reduced the subjective function down to a more simple form. Let's recall again that this is what a typical input sequence will look like after being doctored to fit CM3 for a causal multimodal mask. And this is what a combination of the retrieve document and the query what the combination of the query document and the list of retrieve documents will look like. Note here that the mask can be attached to the mask is within a sequence, and then the mask is attached at the end of a sequence. Having the model emphasize a use on the retrieve documents is poor. One second. The problem with this is that the mask here note here on the mask is within a sequence, and then the definition of the mask is attached to the end. The model for RICM3 does not specify where this mask can appear. In this case, the researchers chose to attach a mask. Okay, motherfucker. Note here, there's a mask within the sequence, followed by a definition for the mask at the end of the sequence. RICM3 states that a mask within a sequence can have a definition for a sequence within a separate text block. It can have a definition it can have a mask within a caption image input sequence, and a definition for something within a retrieve document. The point of this is to emphasize the model's use of the retrieve documents, but the problem with this is it makes it poor for zero-shot capabilities because it's always dependent on previous input. Now, what the developers of Chameleon did was they removed this extra variable that put emphasis on using retrieve documents. They also did some other things to the model, like reducing some hyperparameters that had not yet, at the time of this paper's writing, there were some hyperparameters. Oh my fucking god. Another thing that the researchers did was they removed several hyperparameters. Well, at the time, another thing the researchers did was they implemented some best practices for transformers that had not yet been dispersed yet for transformers, such as removing bias, removing dropout, removing certain layers of the normalization layer. They also modified the dataset a bit. And the effects of modifying the dataset, as well as all these other changes, was rather interesting. In the past, the best results have been encoder-decoder. One issue with those was it's an inability to upscale based on training data. What that means is, well, first here let's look at the scale that they're measured on. The first being this FID scale, which is the similarity of image to image. The lower that this scale is, the lower that a score is on this y-axis, the better that the model is performing at producing images that are similar to what the prompt is asking for. Then we have here on the x-axis the equivalent A100 hours, which just means how long it's taking to train that model. The lower it is, the better it is. Once again, so the sweet spot's going to be over here. For encoder decoder, it starts at the scale starts at 350 million parameters fed into the model to train it. Now the performance starts to increase when we add 750. It's taken a bit of time to increase that performance, and we get to 3 billion parameters. Okay, taking a bit longer, it's getting better too. But now we add 17 billion parameters, and its performance not increasing notably, but the time it's taking to train it, quite considerable. For Chameleon, it's also about 3 million parameters. It's a slightly longer at this amount of time, amount of parameters for this amount of parameters. And as we double the amount, note that the score is dropping quite a bit compared to encoder-decoder models. And then when we get to 7 billion parameters, it's continuing to improve, whereas the previous state-of-the-art would not improve past about 3 billion parameters. Chameleon is continuing to improve. You can look more closely here at what's actually happening by noting here that Chameleon is training at 350 million. Its performance is about here. When it's trained on double that amount, 760, its performance is continuing to increase. Now when it's trained on 10 times the previous, it's still increasing. And its returns do diminish, but the rate that it's doing so is much lower than the previous state-of-the-art. And part of the reason it's doing so well at this is because of something called contrastive decoding, which my colleague Michael will be talking about.
I'm Michael, and I'll be discussing some of the decoding strategies proposed for the generator. Because these approaches can have such a large effect on the quality of the final output during inferencing, several decoding techniques were analyzed, and it turns out that many of them offer complementary benefits. For instance, we have temperature sampling, which involves modifying the softmax temperature to control the randomness of a prediction, and top P sampling, also known as nucleus sampling, which consists of sampling from the smallest set of top-ranked tokens. While individually, both of these decoding strategies produce coherent text generations, if they're paired with classifier-free guidance, the quality of the generated text is significantly improved. Now, classifier-free guidance is a method used by many diffusion models to direct an unconditional sample to a conditional sample. The concept of classifier-free guidance was used to alter the contrastive decoding technique, which I'll discuss some more in detail in a moment. Contrastive decoding top K is a variant of the contrastive decoding technique using principles from classifier-free guidance, which defines a set of potential subsequent tokens based on their probabilities. As previously stated, classifier-free guidance guides an unconditional sample towards a conditional sample. To support unconditional sampling, portions of the text are replaced with a mask token. During inferencing, two token streams are generated. A conditional token stream, which is conditional on previously outputted text, and an unconditional token stream that's only conditional on the mask token. Since the generator is a transformer, classifier-free guidance is applied to logit scores. As you can see in the following equation, the conditional logits are logit scores outputted by the conditional token stream, and the unconditional logits are outputted by the unconditional stream. The bottom equation represents the guided logit scores using logit score used to sample the next text or image token. In this equation, alpha C acts as a guidance scale. Notice the subtraction of the unconditional logits from the conditional logits. This portion of the equation is the reason a contrastive decoding variant is used in the final decoding strategy. In particular, the subtraction resembles the log probability subtraction in contrastive decoding. Contrastive decoding is a search-based algorithm that leverages the differences between large and small language models. Smaller language models demonstrate tendencies to produce undesirable patterns like repetition and topic drifts compared to larger language models. Contrastive decoding is inspired by this observation. The objective is to factor out undesirable patterns present in smaller language models, otherwise known as amateur models, and generate text from the remaining good behaviors of large language models or expert models. This is implemented by subtracting the probabilities of the small model from the large model, which is similar to the logit subtraction from classifier-free guidance, as you can see here. This objective rewards text patterns favored by large language models and penalizes patterns favored by small models. The objective is defined at the sequence level, and since the generator functions on a token level, the following equations were used. The per token contrastive decoding score, as you can see here, is defined as the log probability of the expert model over the amateur model if the token is in the set of new, as you can see here and here. Otherwise, the score is negative infinity. Now, the set new is known as the adaptive plausibility constraint, which is the set of potential subsequent tokens. This constraint is placed on the contrastive decoding method and limits the confidence level of the expert model. This is necessary because amateur language models aren't always wrong. They still capture many simple aspects of grammar and common sense. Therefore, penalizing all behaviors from the amateur language models would penalize the aspects that are correct as well. The adaptive plausibility constraint exploits the confidence level of the expert language model to restrict the effect of the contrastive objective when the expert language model is highly confident in its predictions. Here, alpha is a hyperparameter between 0 and 1 that truncates the next token distribution of the expert model. Larger alpha values mean more aggressive truncation, keeping only high probability tokens, whereas smaller alpha values allow tokens of lower probabilities to be generated. Beam search is used to optimize the contrastive decoding score by first filtering out tokens based on the adaptive plausibility constraint, which eliminates tokens that fail to achieve sufficiently high probabilities under the expert language model. Then the remaining tokens are scored based on the amount of contrast they demonstrate according to the contrastive decoding objective. As a result, plausible tokens are selected under the expert language model that least resemble the amateur language model. While contrastive decoding was a good solution for the generator, some alterations were needed to fit the Chameleon architecture. First, the expert model is conditioned on the previous tokens, and the amateur model is conditioned on the mask token like in classifier for guidance. Additionally, the adaptive plausibility constraint needed to be relaxed. Experiments showed that the strict nature of the constraint would consistently become greedy decoding. These alterations led to the decoding strategy used for the Chameleon generator. In this technique, a new adaptive plausibility constraint is implemented. Instead of taking the largest probability, the contrastive decoding, and like contrastive decoding, the kth largest probability is taken, and this defines contrastive decoding top K. Next, my colleague will discuss the supervised fine-tuning stage of the model.
Supervised fine-tuning. It is an integral part of advancing the model's capabilities. It starts with training the Chameleon model to not only grasp current inputs but also to be agile for future unseen prompts. By amplifying multimodal performance, we are enhancing the model's proficiency across a spectrum of tasks. And the fine tuning of Chameleon was conducted on a curated dataset with which has both images and text prompts. The learning sequence is structured to interleave image and text examples, prompting a more dynamic learning experience. Finally, the fine tuning process leverages the CM3 objective. This objective function strategically integrates the task instruction with the output during training, aligning the model's prediction with the targeted outcomes. Let's take a look at long form generation task. Here is a picture of fries and potato chips. We ask the model which property do these two objects have in common, and it's able to explain in a step-by-step fashion and answers salty. Then there is this another image, and we ask the model to describe all the objects in detail, and it's able to deliver that very gracefully. It says a street sign on the metal pole, trees, cars, everything is mentioned. Now let's take a look at text guided editing. Here we give the model an image of a woman and asks to edit it based on our text prompts. So we ask the model what would she look like as a bearded man, and as you can see both the images are very similar, the only change being the one that we asked, that is the editing of the beard. Here are some more examples where we ask you to put on a pair of glasses, there's an age change and some application of face paint. Then here comes image to image grounded generation. Here we ask the model to extract the open pose from the given image and implement it in the subsequent generated images. And as you can see, the pose is very much similar to what was given to the model. Specially generated grounded image generation. Here we give the model a text prompt and ask it to put the specific objects in a specific location. As you can see, these bounding boxes, it's the bottle, sink, bear, etc. And the model is able to deliver it as per the expectation, that is the dedicated locations that we ask it to do. Image captioning and VQA. Here we give the model to describe the given image and it's able to describe it very well, saying that a man is standing on the beach with a surfboard. Here is another task and we ask it what people are flying and it's able to say kites. Let's take a look at some results. So here is a performance comparison of Chameleon model with other state-of-the-art models across various vision language tasks. So as you can see, Chameleon zero-shot model gives us competitive results against other models having some additional capabilities like image paragraph. While this does not necessarily outperform other models in every single task, this doesn't mean that the model isn't good enough. Rather, it highlights the nuanced nature of model performance and the complexity of multimodal tasks it can handle. Let's take a look at the evaluation dataset. So we have Shutterstock dataset, MS Coco, Flickr 30K, image paragraph, localized narratives, PQA2, WizWiz, OKKI, and Science QA. Moving on to the qualitative evaluation, on our left hand side we have the comparison between different CFG weights and their impact on FID scores. The middle line here indicates the CFG comparison, emphasizing the model's consistent performance in generating high quality images regardless of size. On our right hand side, we see how the number of samples generated per prompt before clip based read ranking influences the FID. Zero shot MS Coco. This table provides a comparative overview of various text to image models on zero shot MS Coco task as measured by FID metric. Chameleon 7B, new state-of-the-art performance on the MS Coco dataset as seen by its low FID score of 4.88, indicating high image quality synthesis. Let's look at the image latency. Here we can see that the Chameleon model, it's able to deliver it in 9.1 seconds, which is very great. Latency is just one aspect of model performance, but it's a vital consideration for user experience in practical deployments of computer vision tasks. Let's take a look at the limitations. So there is still dependency on large-scale data set. Complexity in the model architecture and training is still huge. There are generalization issues. There could be bias in the model because of the data set, and then there are ethical and responsible AI concerns to take care of. Finally, to conclude, we can say Chameleon is a retrieval augmented, token-based, decoder-only, multimodal language model for text to image and image to text generation tasks. It also achieves the state-of-the-art performance in generating high-quality images from textual prompts and vice versa. For future work, could focus on optimizing training process, enhancing the efficiency and scalability. The possibilities are endless in extending these models in zero-shot tasks. Here are the references. Thank you.